Hi, welcome to my channel, JaberTime. I'm gonna go over power rules and I have a list of the powers, as you could see, and the rules and some examples. And also I'm gonna go over 10 examples. I have my notes written, so hopefully it's not gonna take too long to go over. Writing my notes ahead of time will save you some time from watching the video and will make the video shorter. Let's get started. Zero exponent. Anything raised to the power 0 equals 1. For example, 711 to the power 0 is 1. If you have negative exponent right here, the way to do it is you take the reciprocal and you make it positive exponent. Of course, if you have it in the denominator with negative exponent and you want to evaluate that, you need to take the reciprocal, which takes it back to normal log a to the power m. We know that 10 to the power 2 is 100, but 10 to the power negative 2 is not negative 100. The way to do it is we take the reciprocal, it's 1 over 10 to the second, which is 1 over 100, and that is 0.01. You could double check on a calculator that 10 to the power negative 2 is 100ths. Okay? Power of a power rule. As you can see right here, we multiply the exponents to see it with numbers. 7 to the power 2 to the power 3 is 7 to the power 2 times 3, and that is 7 to the power 6. Quotient rule. It shows right here that we need to subtract the exponents. For example, 9 to the power 5 over 9 to the power 2 becomes 9 to the power 5 minus 2, which is 9 to the power 3. Multiplication rule. When you multiply powers with the same base, we add the exponents. For example, 8 to the power 5 times 8 to the power 2 becomes 8 to the power 7, adding 5 and 2. Now here, the rule has it as 8 to the power m times 8 to the power n. It doesn't have to be the same base. It could be two powers inside, and the exponent outside gets applied to both powers inside, as you could see. In multiplication, m times b and n times b, as you could see. For example, I try to choose a different number right here, just to show you that doesn't have to be both 11. 11 to the power 2 times 9 to the power 3, all raised to the power 4, becomes 11 to the power 2 to the power 4 times 9 to the power 3 to the power 4. As you can see, the 4 is now distributed as an exponent to both powers inside, and we keep the multiplication. From the power rule up here, we multiply the exponents. 3 times 2, which is 6. Now here, 4 times 2, 8, and 4 times 3 is 12. That should do it for this problem. Quotient rule, power of a fraction rule. That shouldn't be called a quotient rule. This is a quotient rule. So if you have a quotient, but still we have a power of the quotient. Same idea like the product, we apply the exponent b to both powers inside. We keep them as a fraction. 6 is outside, gets applied to the 15 to the second, and gets applied to the 15 to the third. In multiplication, 2 times 6 is 12. 3 times 6 is 18. We could go further here and subtract 12 minus 8 as a quotient rule, but let's leave it right there, just to show how we apply the main formula. We'll leave the details to the coming examples. Now this one here will be used heavily on the second video after this video when you solve equations. When you solve power functions without using logarithms like in pre-calculus. If you have a to the power m equals a to the power n, this implies that m equals n. Of course, it's both ways. We call it if and only if. Most of the time, in these examples, we're going to be going one way. We will have this. If it's not fully clear, then we'll imply that the exponents will be equal. For example, 7 to the power x equals 7 to the power 3. Well, of course, it's common sense that x has to be 3. It can't be like 11 or 12 or something else. You can't say like 7 to the power 11 equals 7 to the power 3. It doesn't make any sense. So the exponents will be equal if the two powers have the same base. Now let's jump into example number 1. Simplify the following. To simplify this, one way to make it detailed is to think about all these components separate, and we apply the 4 to the y, and we apply 4 to the x, and we apply 4 to the minus 1, as if the coefficient is clearly stated as -1. Here we go. See the -1 to the power 4? You have to be clear with this one. Because it's an even exponent, this is going to end up +1. Just keep that in mind. And here I'm just breaking them down to factors to show you that this is a -1. Now this is a 1, as you could see. I could rearrange these terms or factors in a way to be able to apply the rules clearly. What do I mean? If you notice here, the y's now are next to each other and the x's are next to each other, and the coefficients of this and here, the first one is written or are written up front. One way to say why I could do this, because in multiplication we have the commutative property. 7 times 3 is the same thing as 3 times 7. So we could reorder or permute 7 and 3 in multiplication. That's called the commutative property of multiplication. It's easier to finish this part and finish this part, as we could see. When we apply powers with the same base, we add the exponents. As you can see, we are adding the exponents on top of y, 1y, and we're adding the exponents on top of x as 1x. -1 times 1 is -1. So I'm using the rules that were stated in the first slide, but I'll keep them handy as we go to show you where they're coming from and which one I'm applying. -4 plus 4 is 0. -3 plus 4 is 1. And the first rule that was in slide number 1 was saying a to the power 0 equals 1. Anything raised to the power 0 equals 1. So this is 1. And that does not need to be written as x to the power 1. We agree on it. And the final answer is -1 times x times 1, which is -x. And I did apply right here this rule from slide number 1. So one example down. I have 9 more to go, so let's keep going. One more time. Let's make it clear as factor by factor what's going on here. We have the -1, we have n to the second, we have m to the -3, we have a -1 again, because this negative is not part of the base, and we have m to the power 5. Rearranging one more time, you don't have to, but the way to see it, those negative ones will be multiplied. I have one term with n, and I have two terms with m, so I have the m's next to each other. We're going to add the exponents right here, as we know. -3 plus 5 would be 2. That's a 1. N to the second, m to the second. Clearly without the 1, we don't need to write the 1. N to the second, m to the second. Number 3. Now here we could rearrange and simplify inside before I apply this, because I do have y's and I do have x's. But let's take it the other way by handling the negative exponents and taking the reciprocals, which means we need to have a fraction bar, and that's what I meant. Y to the -2 will be y to the second, x to the power -3 will be x to the third down, and x to the -4 will be x to the 4 down, applying this rule right here. That's an option. The other option is like you just add the exponents right here, then you bring it down, which is gonna give you the same, of course. Now notice right here that 4 and 3 needs to be added, give me 7. And for the y part, we need to subtract the exponent because that's a quotient rule. So we have a quotient rule and we have a product rule. That's y to the third, 5 minus 2, and 4 plus 3 is 7, and that's what we have. We applied the product rule and the quotient rule. 2 steps in one. Now let's apply this to the power of a quotient. 2 will be applied to the numerator and to the denominator. So it's going to be y to the third to the second, which is y to the 3 times 2, which is 6. As you can see right here, we're applying the power of a quotient. 2 times 7 becomes 14, and that should do it. Number 4. Now notice right here that this negative is part of the base. But one way to handle it is bring this down and make it positive. So take the reciprocal of this, bring it down and make it positive. That's this rule. Negative x to the second means negative x times negative x. So the negative gets multiplied by itself, or the negative 1 gets multiplied by itself twice, which is going to change to positive. This negative sign is not part of the base on top, so it's going to stay loose. We bring it up front, as you could see. That is x to the second, and that's y to the 4. This negative is now outside, and we're done. As you could see, if I want to write as I'm recording, it takes time, but look at these writings. It takes some time to write them down. And going over 10 examples with written notes, that's gonna take a way less time to record. So hopefully that's helpful. And now we have 6 more examples to go, but they're not gonna take too long. Here we go. Number 5. So let's take the minus 4 as a power right here with negative exponent, and take the reciprocal and bring it down to denominator. As you can see, y to the power minus 4 is now y to the power positive 4 in the denominator. The only thing on top, I did not write the dot right here, the multiplication, which we agree on since we have the parentheses. I'm applying this rule. Next, let's break this down to 3 pieces, the negative 1, the u, and the v to the second, as 3 factors. Each one of them is raised to the power 4. And that's this rule right here. Of course, negative 1 to the power 4, which means negative 1 times itself 4 times, an even number of times, is going to make it positive 1. So that's what we have. 4 times 2 is 8. We apply the power rule again. And we're going to add the exponents, which makes it v to the 8 and v to the first. Applying this rule will make it v to the 8 plus 1, which is v to the 9. These cancel. We don't need to write one. So the only thing that will stay with us is the v part, and it's, as I said, v to the 9. Number 6. There are similar examples. That's why it's better to have enough examples than just writing slowly, only a few. So let's break it down inside and see what's inside as factors. Same time I'm rearranging. I put the v's next to each other and the u's next to each other. I do have a minus 1 here, another minus 1 right here, which is going to change to positive 1. We're going to add the exponents right here, following this rule. That makes it 5. We're going to add the exponents right here. 3 and 4 is 7. Then we're going to apply this 4 to both factors. That's not going to make any difference for the 1. Then we're going to multiply m times b, as you could see from this rule. So 4 gets multiplied by 5 and 4 gets multiplied by 7. 4 times 5 is 20. And 4 times 7 is 28. And that should do it. So I'm applying this rule right here. Number 7. Same thing. Let's break it down into factors inside. I have two minuses. Minus 1, minus 1. Regroup the m's together and the n's together. Add the exponents. 3 plus 5 is 8. Negative 2 plus 3 is positive 1, and that's a positive 1. Applying the 4 to both, that's what we're going to end up with. 4 times 8 is 32, and 4 times 1 is 4. No need to write the 1 up front. And if you need more about why I'm doing things like that, I am stating the rules right next to each step. Number 8. Let's break this down to two factors. 2 as an exponent on top of x to the first, and 2 as an exponent on top of y to the power negative 2. That's this rule right here. Next, 2 times 3 is 6. 2 times negative 2 is negative 4. Let's rearrange. Put the y's next to each other. That's the commutative property of multiplication. Let's add the exponents right here, 6 and negative 4, which makes it 2. Applying this rule right here. So it's y to the second, x to the second. 2 more. Number 9. Applying the power of a power. Negative 3 times 3 is negative 9. Add the exponents using this rule. Negative 9 plus 12 is 3. The last example, number 10. X to the power negative 3 times y to the power 5 to the second. Let's bring this down to the denominator. That's called negative exponents. We take the reciprocal, or we bring it down. Let's apply 2 times 5 using the power of a power rule, and that should do it. So 10 examples with introduction. It's about 18-19 minutes. That should do it. I do want to go over 25 or half an hour, 25 minutes. I think that was not too fast, showing you enough practice. After this video, I have another one pretty much similar, but with equal sign. It's called solve exponential functions. So if you need more practice, that's pretty much the same or similar topic, but has more into it because we have an equation and we need to solve for the missing variable. Thank you. Thank you for watching. If you like this video, hit the like button and subscribe, and I'll see you next time. Thank you.